In this next part of section 2, we're going to be looking at piecewise defined functions a little more closely. We did see a piecewise function in section 1, but here we're going to be using the parent function shapes that we created to illustrate how the piecewise function can work here. So example 2.2 is going to define for us a function. And I can see that it's a piecewise defined function because of the way that the equation is given to me. Right here is going to show me that it's a piecewise defined function. There is two pieces. We have a top piece and we have a bottom piece. You're not restricted to only having two pieces, but in order for it to be a piecewise function, there has to be two or more pieces. So you could have 3, 4, 5, as many as you'd like, I suppose. And what we want to do is look specifically at what type of equation or what kind of shape do we need to look at for the different pieces. So the first piece is what we'll focus on here at the beginning is given to us by x squared. Well, that's the squaring function. And we should have a picture of the squaring function already available. If you don't, let me pull up a picture of the squaring function. And we can see here the squaring function is our parabola shape. And on that top line in the equation definition there, it says that we're going to be using the squaring function if x is less than or equal to 2. So I want to focus on where x is equal to 2. So looking at my graph, here's where I have 2 along the x-axis. And if I take that and carry it up to the curve, there is one point in particular that I need to be looking at. And that point right there is the point at 2, 4. And that takes care of the equal to 2 portion of that top piece. But we also have the less than symbol there. So with the less than symbol, I want to take the point that I started at and I want to then copy the rest of the ordered pair that are to the left. That would be everything that is from 2 and less than 2. So I don't want the entire picture of the squaring function. I only want a piece of it. Hence why we call this a piecewise defined function. So going over to the blank graph for this example, I'm going to mark the point at 2, 4. And I'm also going to mark some of the other points that I would normally mark when I'm graphing the squaring function because they're all to the left of my starting point. And then I will graph, starting at 2, 4, the parabola shape. And that's the only part of it that I want. So that's the first piece. The second piece, if I clear out some of this here, let's give ourselves some space. The second piece is right here. And the equation that we're looking at is x. This would be the identity function. Let me pull up a picture of the identity function. There it is. So with the identity function, we are again looking at this condition. It says we're only going to look at the identity function if x is greater than 2. Now I know it doesn't say equal to there, but I still want to look at where x is 2. And if I go to where x is 2, I can see that it's this point right here, located at 2, 2. But since I don't actually want to include that point in my picture, what I really should do is put an open circle there. Think of it as being an open circle there at 2, 2. And then looking at the inequality says that I want x to be greater than 2. Well, greater than 2 is going to be going to the right. So that if I'm going to the right on the identity function curve, that's going to take me in this direction, going up and to the right. So coming over to the grid that I originally started with, I want to put the second piece on the graph along with the first piece. So I'm going to come over here to 2, 2, and I'll make my open circle there, and then I'll graph the rest of the identity function, and this is the graph of f.